The next speaker will talk us about the Belgian MYRRHA project. It's called MYRRHA, a flexible and fast spectrum irradiation facility. Speaker is Hamid Abderahim, the Deputy Director General of the Belgian Research Center. Are you set up, Hamid? And also get your talk. It's still the old talk.
Is this working? I don't know. Yeah. Okay. Thank you. Okay. Good afternoon, everyone. I hope that you will forgive me a bit because I didn't put any thorium in this machine yet. But you have seen that at our place, we are having studies on the thorium, plutonium oxide fuel. We are cooking presently TOMOX fuel in the BR2, where we will be reaching 30 gigawatt day per ton burn up. So we are continuing experiments on those kind of fuel. This means that we are interested in this. You have seen this morning, this afternoon, or this morning, sorry, before lunch, some of the results reported. And if you are interested to have information on this, we are ready to share. Now, about MYRRHA. I think from the talk of Carlo this morning, we have seen clearly that we can speed up the thorium cycle thanks to the ADS system. It can also be a machine for producing energy. The difficulty, and I see when in various talks that we have mainly records of the past programs, so we need the new programs. And to justify to the taxpayer today that he has to spend €1 billion for a program, you have to give him something back. So that's what we try to put together in this project MYRRHA, that we say we want to advance this idea of ADS. And I would say that we have, honestly, to give, I would say, reward to Carlo, who waked up as in 93, 94 for this idea of ADS, and that we were maybe have forgotten or even have never thought the engineers, nuclear engineers guys, those strong guys that are building reactors, etc. And we were not able to come with new ideas. That's the big problem we have in our community. And so, to my opinion, we should not bother Carlo when he is making his presentation on those systems about telling him how you cool down this system. It's to the engineers to solve that, and that's what we have to do. And I think that what we try to do here, transform these ideas into an engineering product and something that you can build. So MYRRHA is 65 to 100 megawatt thermal. So the total maximum power of this machine is 100 megawatt thermal, but we can operate at lower if we don't need that 100 megawatt because it's a research machine. It's just like our BR2 today. It's 120 nominal power, but we operate between 60 to 120. It's subcritical, deep subcriticality, 0.95, to avoid any discussions about going beyond the criticality with our safety authorities. We have undergone this because we have already an operating ADS in MOL with a lead core containing 1.5 tons of fuel in it, but operating at 500 watt coupled with a deuteron generator, fully licensed, built, and put in operation. And so we learn from that licensing for this machine. And to operate this subcritical reactor, we are using a linear accelerator delivering 600 MeV, 4 milliamp. We don't need all those 4 milliamp to operate MYRRHA at the level we wanted. We would need 2.5 milliamp. But we want to over-design it in order to improve the reliability. So the accelerator we have is proton accelerator, 600 MeV for milliamp, but operating in CW and not in pulsed mode. The challenge we have is this one, the number of failure that we are requesting from our accelerator. We intend to operate Mira 3 months in continuous, and then we shut down for 1 month for maintenance, preventive maintenance, and loading experiment in the reactor. A second cycle, 3 months, 1 month, and a third cycle, 3 months of operation and 3 months of shutdown for really heavy preventive maintenance. And so the beam trips, we request 10 of them longer than 3 seconds per 3 months of the cycle. This means 3 shutdowns or beam trips larger than 3 seconds we accept per month. And this is rather demanding. Shorter beam trips, we are not concerned because the thermal inertia of our reactor can take that. And so if we shut down and we restart instantaneously, we don't care about that. So is this reality or we are dreaming? You see here the request of Mira, 3 seconds. We wanted this level of number of trips per day, so corresponding to this 10 per 3 months. And today, if you look to the two, let's say, spallation sources, the SNS of Oak Ridge or JAEA JPark data, what you see is that we have still 2 decades to win to get to where we are aiming at. So this is the challenge we have, and how we are addressing in the design of the accelerator of Mira this. First of all, at the low energy part, we have duplicated the injector up to 17 MeV. We have 2 injectors. We are not working with both of them at the same time. One is on standby that we switch on when we lose the one working. After that, we have the spoke cavities and then the niobium elliptic cavities, low beta, high beta. And what we adapted is what we are calling the fault-tolerant design, means that we can lose some of the cavities and we retune the adjacent ones in order to get the final energy we are looking at the end of the accelerator. And during our maintenance, we will be retuning the cavities that we have lost. So during the operation, we don't touch that. We just retune the adjacent ones. And so there will be a special talk on the accelerator of Mira during this conference. At the end, we have the full beam dump that takes the 2.4 megawatt. And then we go up and down, enter from the top of the reactor, the beam into the center of the reactor. There is still, you see here, about 20 meters. So for the last beam optics, there is also a challenge because the footprint of the beam is about 6 to 7 centimeters in diameter, and we want to put it in a position, let's say, with a deviation of 1 to 2 millimeters, whereas we are at 20 meters here. So the reactor is a classical, I would say, fast reactor system with a vessel. But I will invite you to enter in that vessel, which is about 6.5 meters in diameter, 11 meters in height. It is with a plug, a lead of 2 meters thick, with all penetrations for all the components that we can actually extract from the reactor without opening it. We can discharge all the components of that reactor out of it without opening the lead, except one component I will show you later. This is the core barrel, which is about 1 meter in diameter. It is made of steel, ThEC13, and we have here the core, which is about 2 meters in height and 1 meter in diameter. I will come later on the detail of the core. In the center, we have the beamline. Before, we were designing a windowless target that had a separate circuit for cooling the target. Now we are having a window target, which is simply the central tube, and we shoot our proton beam directly on the coolant of the reactor. We have made some experiments that the amount of spallation product that we can generate are not making our life more complicated than if it was in a separate circuit. The damage on the structures which are closer, the fuel, etc., is also negligible because the main stream of the neutrons are forward peaking, so going to down, so they are not irradiating the lateral part of the containment of the fuel. Then we have all these structures above the core. We need, I would say, temperature control, flow control in each assembly, if there is a leaking assembly, etc. We have also, as I said in the beginning, this can be also operating in critical mode. Why? We have done that because in the licensing of this small ADS, Guinevere, our licensing authority requested to have also the critical mode because that's what they know as a reference case. Okay. We have yes, we can be not agreeing, but we have to do with them. And so we put the control rods in this, and it doesn't disturb us that much. And okay, the advantage of the lead or lead bismuth is the non-reactivity, chemical reactivity with water. So we allow to put our heat exchangers inside the vessel. And the secondary fluid we use is boiling water. Two primary pumps, mechanical ones, which we have designed with special material for the rotor of the pumps. And we have built a mock-up of this pump, and we are testing it under liquid metal. We have these, I would say, the bidule to produce silicon doping because, as I said, you build a machine, you need money to operate it, so put some commercial activity in it that brings you money and will leverage the operational cost. We are doing that in our BR2 reactor. We produce 30% of the doped silicon of the world, and we produce between 25 to 60% of the radioisotope of the world. We just continue our business as we are doing in BR2. This part is what we call the diaphragm, which is separating the cold zone of the reactor from the hot zone. So the fluid is pushed down through the core to cool it. The inlet temperature of MYRRHA is 300 degrees C, outlet temperature 420. We can do that thanks to the fact that we are using lead bismuth and not pure lead. I agree with what Carlo was saying this morning. To my opinion, on the longer run, we have to think lead. But should I wait up to I make those new materials that will be making me working at higher temperature? Those materials do not exist from the shelf today. So I think we can afford for a research machine to make it with lead bismuth, but without forgetting that the final objective, we have to go to pure lead, and so develop the needed materials that can sustain higher temperature. But here we have gone lead bismuth because of this constraint, and the corrosion is less, I would say, problematic at those low temperatures. So the core is made of hexagonal assemblies. You see for 0.95 as a K effective, we can reach that with 69 fuel assemblies. You see those green dots, these are the control rods. As I said, we were asked to be also able to operate in critical. We put control rods. And the control rods are inserted from underneath. Just like the fuel, we are loading the fuel from underneath. Why? Because lead, or lead bismuth, is a very dense metal. So it's heavier than what you are putting in it. Instead of pushing all those elements and hold them there, just let physics work for you. Put them from underneath and they will be floating by buoyancy, they come in position. And so that's what we did. But nevertheless, the safety rods, those three guys here, they fall in the reactor by gravity. So they are with a ballast made of tungsten, and they can then drop even in the lead bismuth, and we are testing what is the time to get them in the system. We have also a crown of assemblies with yttrium zirconium oxide to act as a reflector. You save fuel if you are reflecting neutrons, and you are protecting the barrel of your fuel, so the DPA is reduced in it. And then this is an experimental machine. We have plenty of experimental positions. These yellow dots, the central one will contain the spallation target, or if we operate in critical, it can become an experimental position. The other ones are experimental positions. And what is the advantage of those particular 7 positions? They are accessible through the lead. This means that we can put conditions of irradiation which are completely independent of the condition of the reactor. I can change the fluid there. I can change the temperature as I want. I can have a separate control of the temperature. And this is then giving a very big flexibility for these irradiation channels. And the other ones, are also positioned to make irradiations, but at the conditions of the reactor in terms of temperature. The fuel assembly is made of MOX fuel, 30% of plutonium, a vector of PWR reprocessed plutonium, so containing about 61% of fissile material, and so 60 times 30, 18% of fissile material. It's 60 centimeter in length. The fuel assembly is about 2 meters. To hold the fuel pins, from each other, we don't have a grid, but we have a wire which is elliptic around the fuel pin, because to avoid corrosions of those grids and shocks and vibrations of the grid that can damage the fuel clad. The fuel clad for the 2 to 3 first cores will be the 15-15 titanium stabilized. Normally, we are intending to use also for the clad the T91 ferritic martensitic steel, but we don't have the data of irradiated material. So therefore, we have the data for this. We will use for the fuel cores this type of material. The wrapper and the wire are made of T91. It's not a big issue. The decay heat and what Carlo was talking, AirVacs, it's implemented in here. We have the heat exchangers that are operating as independent loops, 4 independent loops that take 100% of the decay heat of MYRRHA. But they are all the 4 the same. If we have a common failure, then we are done. So therefore, we added an extra system which is completely independent from the other one, which is based on cooling through the air, which is circulating by natural circulation. And this can work with lead. It can't work with sodium, because the lead heat capacity. So some solutions can work with some technology and not with every technology. Here it can work. And so this is also something that engineers should be also looking when they make their choices. So the reactor building, so this is the containment building. This part is like an alpha cell because of the polonium, indeed, which is alpha emitter. So it's like an alpha cell, the containment of the reactor. You see here a second pit in the reactor building where we can extract all the components and park them in this second pit, so we can empty fully the reactor. But Mira is, first of all, intended for this. You know, I will not enter in this, reducing the time life of the radiotoxicity. But it's not simply going alone. Mira contributes to these third building blocks. We need this advanced reprocessing, which is going on in Atalante, among others. And we need to go to, I would say, a level beyond the lab scale. We would like to be able, today we can treat batches of 50 to 60 kilograms. We need to go to 1 ton. Here, Malab, Mr. Didier Haas was presenting this morning. He was the one who put together the Malab, minor actinide lab of GRC ETU, able to handle 20 grams of americium, 4 grams of curium. This is not sufficient. 1 fuel pin of Mira contains half a kilogram of minor actinide. But now, ETU has upgraded its facility to 200 kilograms of minor actinide and plutonium. So we are in Europe having something that allows us to do things now. The third block is these dedicated burners, and one of them is the Mira. But not to forget the advanced fuel containing large amount of minor actinide, we need specific reprocessing. And I think the pyro reprocessing or whatever is the way that we have to go. We can't treat that with our classical water reprocessing. If you have to wait 10 years between you can handle it, to burn 1 core, it takes you 100 years. This is not acceptable. This you know, I don't spend time on that, why ADS, etc. But what is interesting in Europe, why we are looking to the ADS? We have different policy country by country. Countries willing to continue with nuclear, country living nuclear, and they have the problem of the nuclear waste on their table. We think that if we share those specific facilities like the ADS fuel fabrication, the ADS fuel reprocessing, thanks to pyro reprocessing, for instance, and then the burning in this ADS, where you can concentrate the burning. So that makes sense for different national policies. The advantage for those quitting nuclear, they get rid of their minor actinide in a smaller number of machines, and they share with others. The guys willing to continue, these guys, they will not mess their park of electricity production with potential dangerous product that I am scared of. I will put them really in my production park. This is nonsense. So this is the added value. I will just go very rapidly. I said this is multi-purpose research facility. We can do irradiation of material in those positions I showed you, accessible from the lead. And you see the amount of DPA per year we can achieve, the level of flux, total flux we have in there. For material for fusion, we can even put in the flame of the spallation neutrons under the spallation target a special device that we have developed for hosting the samples, material samples, and we can put them from underneath the same way we put the fuel assemblies or the control rods, whatever. And we can put them in a very controlled environment of temperature, and also a range of temperature can be defined. And what you see is this. This is what IFMIF is intending to deliver. So the holy number for fusion people is 10 ppm helium per dPa. This is the characteristic of the spectrum. That's what they are aiming at. And with a dPa for the first wall, about 20 to 30 dPa per year. So this is the demo, what they are requesting for the first wall. And so what we have seen and shown that Mira can deliver this kind of values and even going beyond up to 25 ppm helium per dPa and a range of dPa, which is this one. I speed up I said we can produce molybdenum, and this is the case here. One thing you should know about molybdenum, you need 2 curie per gram that you are having a good product. If you have lower, yeah, well, the molybdenum is the one you have to produce, and then that's the father, indeed. So, but you have to reach this level, then you are interesting. If you are below that, it's not commercially interesting. So Mira is in the roadmap of Europe, etc. So this is the big partner network we have, and we have a large amount of Belgian guys with us. But beyond the Belgians, we have also a series of research centra, academia, and also beyond Europe, we have partners in there. This project is supported by the government of Belgium through 2 ministries, the economy and the Belgian policy. And through the European program, in various topics, actually, we have benefited in this project through various projects, like Freya is going on today in Guinevere. We have Matter for material, the fair fuels for specific fuels, CDT, Central Design Team, that was hosted in Mol to design further Mira, etc. So we are really having good interaction with our European colleagues. What's the situation today? Mira cost 1 billion euro of 2009. We are investing heavy money from our own money from SCK, but the Belgian government gave us an extra 60 million euro for the period 2010-2014. In 2014, we have to make an evaluation. Belgium wanted to invest 40% in this facility, and we look to international partnership from outside. Where we are in terms of planning, so we are here today somewhere, and we have to fulfill this by the end of 2014, 2015. We have to do the front-end engineering design. Just 2 weeks ago, we have awarded the contract for an international European consortium for completing the engineering of the auxiliary systems of Mira. This is 24 million euro that we gave as a contract for a group made of Arriva, Onsaldo Nucleare, and Empresarios Agrupados. And also for supporting all these systems, we have built a series of labs. And you see that we have different facilities that has been built. And also one aspect that was touched this morning, we know that polonium is an issue. We built a specific lab for the polonium behavior and how we can, is it staying in the lead bismuth? Is it getting out? If it gets out, how you catch it, etc. So I think I finish here. I don't have too much time anymore. So that's what Mira will look like in the center. So this is the reactor building, the front end where the injector are, and the accelerator 250 meter long. This is our BR2. The design team is sitting there, and the support program is conducted here. Thank you very much.
Okay, thank you very much, Hamid. Maybe your transparency with your conclusions, but I think you made your point very well. You can put it on and people can read it. Thank you to have allowed by this last shortcut some discussion time. Yes, I see Carlo who wants to take the first shoot.
My usual question. I have 2 comments or questions for you. First of all, you are concerned about the number of trips from your LINAC. You are not aware of what's going on in high energy physics lab, but it's one living example which gives indication that your expectations are certainly very favorable. Let's take LEP. LEP is a machine which was built here at CERN, 37 kilometers circumference. There is a radio frequency there with cavities which are not very different than yours. And those cavities are DC cavities running continuously like yours, and they have about 3 GeV total gain. So it's a huge gain. Mm-hmm. Now, if one of these cavities, that positron and electron in there, and there are currents of the order of 7 milliamps, which is much larger than your current, 7 milliamp positrons, 7 milliamp electrons, loses the current for an extremely short period of time, for a few milliseconds or even less, then the synchrotron radiation will make losses to the beam, and the beam will get lost. So even if the smallest loss in time of the superconductivity cavities would cause the loss of the beam. Now, the beam of LEP has been running for many years, and has been running with a lifetime of the beam with very negligible disasters of the type you say, with a lifetime of about 24 hours. So we know that it is possible to obtain those things and get the rate of failures much smaller than you assume. This, I think, is an important question. Similarly, the same thing applies also to the LHC. In the LHC, you have a lot of cavities as well, and if you lose the beam, if you lose the current, you lose the beam because the beam then gets lost because of synchrotron radiation and phenomena like this. And this is again something not so important as LEP, but it's still something is important. So I think you should be very optimistic about that point. Second point I'd like to mention here relates to your situations with using of your molten lead and with the solution of using lead bismuth. In my view, you should argue whether it is possible to put a molten salt in there. Can you run with a molten salt instead of molten lead bismuth? Because the lead bismuth is extremely dangerous because of the things you know, and in fact it cannot be applied very easily for a practical application. And it would seem to me that instead of having a metal, you will put a salt there. Probably this is something you have to find out, but you may be able to run. And now the advantage of that we already know that molten salt will operate safely with the proper stainless steel materials. It was done 5 years of running and so forth and so on. So you may be able to survive in a better way. So one of the questions is whether you can look at that solution as an alternative.
Maybe I'm allowed to make a small comment to the.
You are the chairman, so it's your responsibility.
I wanted just to say that as chairman. First of all, there will be a specific...
But even the chairman has to use the mic.
Yeah, absolutely. But this is the people who... How it works. You have this special accelerator session where we will discuss exactly this point. But I think Hamid is optimistic enough. You are right to say he should be optimistic because, indeed, Hamid works mainly with the people who have actually built a major part of LHC, who have contributed to the lab and so on, and who are aware that the European synchrotron radiation source has, just since a few months, exactly the ADS specification. So we tell him all the time,
very good.
As
so
you
one more point.
Be optimistic, Hamid.
Yeah.
The second question is you.
Thank you for this. And I would like just to add that just this afternoon, we have formalized an agreement with CERN on the collaboration for the accelerator of MYRRHA, because we know that we can learn a lot from what has been achieved here on the reliability and the development of the components for MYRRHA. So just this afternoon at 2 p.m. we were signing that, and well, we are confident, but I try to refrain my enthusiasm sometimes because some people were a bit scared that I am telling nonsense.
But now quickly to the other very pertinent
the other
question,
one,
please.
Yes, I will have a look to using molten salt. But to my opinion, one of the issue that we will have, I don't know about the spallation target, we should have a heavy liquid metal for that. We can use the molten salt also shooting directly on the molten salt, or then we have to go to a specific module for the spallation target inside that molten salt. That's one aspect, but I will check this ID. I know that it can work indeed, but up till now we haven't looked at because of this link we are making that the same liquid is used for the spallation target as for the
Yes, but the
cooling.
spallation target could be some other material. It could be a metal.
Yeah.
It could be tungsten.
Yeah.
It could be some kind of very long, very heavy metal, which will remain solid.
Now that we looked, Carlo, with the power
Depends
density.
how big the beam is. I mean, we can discuss it.
Yeah. We tried even to
You can spread the beam.
spread the beam.
Okay, let me, it's indeed the most important issue. Let me just tell you that we have started now in CNRS the simulations in Nantes, where we use a concentric target with an outer and an inner fuel core. And this concentric target would likely be indeed solid. We are back to, and then we get a much more simpler ADS, and we get an ADS which would have 3 gigawatt of thermal power. So one single ADS for the whole French fleet, for example. Okay, but we need also some other, 2 more questions, and then I close the session because of our coffee break.
Hamid, you don't mention too much the ADS aspect of Mira. You mention as a irradiation facility aspect, which is the fast reactor irradiation facility. Yeah. How much of the ADS work is going to be done?
It's continuously ADS, because I am making an ADS that at the same time irradiates material, fuel, whatever you want. But it is operating as an ADS.
No, but you'll be loading some actinides from other places.
Yes, that's for sure. And the design of the core is made so the safety margins of that core can accept up to 6 full fuel assemblies of minor actinide with different compositions without jeopardizing our safety margins of the facility. Mm-hmm. And we can also put various targets with thorium, or even I can put one of those impile section, I call it, a molten salt system in that impile section without any problem.
Okay. There was first a question. I have to respect the order, please. There was first a question. Initially, I said this would be the last question, but you will get the last word.
No, it is only one question. What is the efficiency that you expect electrically for your accelerator? It means how much electricity power you have to put to get 1 megawatt or 2 megawatt?
For the moment, we are estimating it will be 10% efficiency, but we would like to improve that. But for the moment, our business plan for the cost operation of the machine is based on 10%.
Yeah, the design is by no means optimized to produce electrical power, but still it's self-sustained.
Thank you, Carlo. But I have to sell things that I can afterwards be able to operate. So for the moment, I'm making my business plan for the cost of operational cost based on 10%.
Okay, last question.
No, I just wanted to know, I saw you have some 6 or 7 targets there, target locations.
No. The target is only the central one. The other yellow dots you have seen, these are experimental channels that are accessible through the lead. Okay. These are experimental channels. Only the central channel can hold the spallation target.
Okay.